Okay, great. So does anybody have an idea of why I'm talking about probabilities and why I'm making you flip coins as an introduction technique? Yeah?
Well, when we're analyzing our data sets, it's never an exact answer. It's always a probability that a certain hypothesis might be a no or not no.
Yeah, that's exactly right. Because we're talking a lot about p-values, and your homework this week is going to be all about p-values, which is probability values. So they're related to probabilities. And just like here, if we analyze these data, this is not quite enough. When we have a lot of people, this is a lot of data, but you know, if this was 100 of you and we had 40 correct and 70 incorrect, we might come to the conclusion that the coin is biased, or that we are always more likely to be wrong than not wrong. But that's just chance random fluctuations in our data. And so we want to make sure with our p-values and with our statistical tests that we do that we're not capturing random chance, but actually capturing some true signal. That's why. Yeah, okay, great. So now let me get to this lecture-y guy. I've been through most of your responses on your surveys, but I haven't responded to everyone yet. So if you don't have a response from me, you'll have it by the end of the day. I appreciate your filling those out. I'm excited about the semester. Come on, start. Okay, so now let me see. Hey, folks at home, Susan and co, can you all talk to me about what you can see? Do you see a notes page, or do you
We can see the whole notes page in the next slide, and no notes in slide 2 of 84.
Alrighty, let me see if I can swap over what you see. Let's see if I can. How about now?
We just see the slide.
Woohoo! Progress. Thanks for the growing pains, sticking with me guys through this. I appreciate it. Okay, so the first thing I wanted to do is talk about the results of this survey. One of the things I asked you is, how do you want to meet? And almost everybody said just a mixture of in-person and Zoom would be great. So I'm going to stick with a mixture of in-person and Zoom. I'm going to try to tell you exactly a week out what it will be. So by the end of the class period, I'll let you know what our class period will be like for next time. And it looks like we have at least one person who's like, oh my gosh, please be in person or else I'm going to lose it. So we'll try to do a lot of in-person, and we'll still try to do a lot of Zooms. I'll always have Zoom open too, so if we do have an in-person and you can't make it, you're not feeling well, your schools are canceled, who knows? All kinds of weird things are going to happen this year, so Zoom will always be an option, as will be the recording afterwards. Okay. Next, I wanted to go over these just to show you that when we're talking about statistical interactions is going to be a lot of what we talk about for the next, not next week, but the next 3 weeks after that. We're going to do a lot of statistical interactions, so because we have a little bit of a learning curve here, it makes a lot of sense how much time we're going to spend on that. The next is, this is part of the, this survey here. I cringe when I think about statistics, is a math anxiety scale. So it's one of the many measures on one of the many indicators on a math anxiety scale. So I put these items here to let you know that I'm aware that people freak out about statistics often, and I'm here to help you get through that emotionally and, computationally, both. These are the next 2 items here from that scale, and you'll see that we do have quite a few people who are saying that they're feeling a little bit anxious about this class, essentially. Just feeling anxious about statistics in general. So again, I present this to you to show that I'm aware that this happens and that I've tried to design this course in order to make that not be such an issue. All right, so the next thing I want to talk about is quantitative data just generally. We have a lot more CREM students in here than I have in my typical class, so you all are much more used to quantitative data, I think, than many people are. But I want to talk about what quantitative data are. So here's some examples of quantitative numbers. For example, OSU has a 2% positive COVID test rate in the last 7 days. That was something I looked up this morning, just to add that to our slides. Another quantitative number here is there are 68,000 students enrolled at Ohio State, or there are 154 regular season episodes of The West Wing. So some of these numbers are easier to interpret than other numbers. Can you think of, like, looking at these numbers, like, which ones of these seem like, oh, well, that's easy to quantify, versus, well, how did you actually get that number?
Enrollment seems very easy to quantify.
Yeah? Does anybody study? No, we don't have any higher education studiers here. It does seem simple to quantify, except do you count graduate students or not graduate students?
I count both.
Yeah, I actually don't know which number this counted, whether it was one or both. That could be simple. Positive test rate in the last 7 days, I feel like, is a little squishy. Yeah, go ahead.
Yeah, I was gonna say like percentage is harder to interpret because you don't know like what it's out of, like the total number of students.
Right, you don't know how many were actually tested. I think it was something like 154 tests. But that can't be because it says 154 regular seasons of The West Wing. So I think I may have just remembered that wrong. That would be too much of a coincidence, even for us. This is pretty easy to count, so that's pretty straightforward. I also defined it more clearly because I said 154 regular season episodes, as opposed to this, was a student is a full-time student, or is it only half-time students? I didn't actually clarify. Here's another, one of my most favorite examples of why quantitative data are important and why you have to have good measures and good definitions of your measures, because looking at the healthiest science on the internet, this doesn't really, no variance here on this variable. They're all 0. Okay, and here's one more example where I want you to, I'm going to ask for your contributions here. Folks at home, you too. So if you read this quote, which is from I guess that must have been January in 2020 or 2019. It says 75% of respondents rated Donald Trump's State of the Union address as great or historic. If you read just that quote, that headline, what are the conclusions that you might draw?
People don't know how to do surveys.
People, you're probably exactly right. Yes, go ahead.
I was gonna say they might have carried out this survey at my family reunion.
So that's it. You've got some conclusions about who's taking the survey. Yeah, what do you have, Lola?
I mean, they could be pre-wording, like, did you think it was great? Did you think it was historic, rather than letting them fill in a blank?
Yeah, it totally could be. Yeah, go ahead. Bring it
Also,
on.
great and historic are not, like historic can be bad. And so, like, I feel like great could be one end of the scale, while historic could be the other,
Sure.
if it's a poorly designed.
Historic would be sort of like remarkable, incredible. Any of those could have alternate meanings.
I think it could be misleading, especially if you see this in the front of a magazine or a newspaper. People might be more willing to think that Donald Trump is the greatest person ever as a result of the survey.
Yes, I agree with you. These are a little bit snarky, but this is actually probably what people are taking away. With just this one statement, I think you're right. It's saying, wow, this must have been a really good speech. Wow, he must have done a really great job. And maybe you're undermine, you're thinking, yeah, but like what? And I'll show you why that's valid. Anybody at home have one you want to share? At home? I'm sorry if you're not at home. Anybody on my screen? That's very self-centered. No? Okay. So let me show you the actual survey. This is actually real. So when he sent this out, the poll had 3 options. It was historic, great, or good. So 25% of people said good, and everyone else who responded said historic or great. So now that you know that, does that change the kinds of conclusions you're able to draw about this survey and about this finding?
I mean, I guess kind of like what she said, it seems like it's a biased question.
Yeah. I totally agree. It's a very biased question.
Something that I was thinking with the main question, who are the respondents? So what was the pool that they took the respondents from?
Yes.
Something that we need to know to get conclusion.
Absolutely right. And I had the same thought, which is why I looked around and I found this. I don't know if you can read this because it's really small. It says, Trump's State of the Union polled well because Republicans watched it. The State of the Union audience is generally skewed towards the president's party, especially the last one. So that was the conclusions there. So you might ask, having seen this, well, this is a pretty biased question that's been asked. I don't think that conclusion generalizes to the population as a whole. It generalizes to maybe people who watched it and people who already support the president, the former president. Also, we don't know how many respondents there were. 75%. Could have been 4 people who filled out that survey. I can't do math, but we had 70% wrong on our coin flips. Ish. Right, 7 out of 11, 70-ish%. That looks pretty bad too. So knowing the total number of participants is also really helpful. Okay, so I bring all of this up as sort of this talk about quantitative data. Oh no, I missed one. Yes, exactly. Only people who approved of Trump's speech may have completed the survey. So I bring all this up to just remind you that data don't know where they come from, and that it's up to you to be the interpreter of those data and to be as truthful with those data as possible. Here in the scientific world, we would want to report that results of that survey very differently than someone on the president's campaign might want to. I also bring this up because it's really easy to think that quantitative data are facts and factual, and you'll hear that a lot, that equating of it's just the facts, it's numbers, it's truth. And I want to make sure that you have this example, a counterexample of how numbers are not just facts, and they aren't just representing truth. It's a much bigger, it's a much more complex concept than just a fact. And particularly when you think about statistics, what we are learning to do in this class and what you'll go on and learn to do in other statistics classes and what will happen in the papers that you read is people are taking these quantitative numbers and they're doing more and more complex things to them and then spitting out a number and trying to draw a conclusion from it. So it's your responsibility as the person who understands what is happening to these numbers to A, understand what's happening to the numbers, and then B, to interpret it in such a way that's truthful and that best represents what is really happening. And sometimes that means saying, we only had these 3 options. This is what they said. And so you draw a very different conclusion. The conclusion you draw from that State of the Union poll is, of the right-leaning supporters, many of them rated it as historic or excellent, but please be aware that there were no options to say it was not good. So that contextualization is your job. So the percentages is sort of an easy example. When we're doing t-tests and regressions and GLMs, that's a little bit more and more and more complicated. But the same principle applies. It's up to you to know how those numbers work so you can best truthfully represent them. And I bring all of that up because I don't know how much you have heard about the history of quantitative data, or if maybe you have people in your life who are qualitative researchers, but you may hear that statistics is racist. That is something that you may have heard, and when you told people, I'm taking this quant class, people might have said, why? It's racist. Why would you do that? And those people who have said that are absolutely right. The history of this statistical method is that they really truly were developed to elevate white supremacist ideals. And I think it's really important that everybody learning statistics be aware that this is the case, so that hopefully we don't do it again. So for example, these founders of modern statistics, they were all members of something called eugenics. The idea of eugenics is through proper breeding, we can make everybody more like white Europeans. And they literally developed all of these statistical tools that we're learning about. They developed them on purpose to show that white Europeans were better. But they do that to look at heritability of undesirable traits, but they decide what's desirable. So they say, okay, having blonde hair is the best. So now let's see what percentage of people who are in Europe have blonde hair versus percentage of people in Africa. Oh gosh, it's so much higher in Europe, therefore Europe is superior. So here's another excellent example of terrible logic applied from quantitative just fact statistics. There are more black people in jail than white people, therefore black people are more likely to commit violent crime than white people. That's a terrible use of facts to argue for something that isn't true, to use the data falsely and for a bad purpose. So I bring this all back to the idea that data don't know where they come from. You have to be the one that interprets the data and knows where it comes from. Your mini ethics course at the beginning of this class. You're the interpreter, that's up to you. So a lot of the work that we do in this class is going to focus on interpretation, because I want to see that you understand what's happening to these numbers behind the scenes, so that you're not making a mistake similar to what's happening here. Once I have a fact, I can make a poorly logical out conclusion. Okay, before I move on from that section, I have put in your module for this week a reading specifically about the racist history of statistics and quantitative methods, which I would encourage you to read. They're really short, they're like a page long. I think there's one or maybe two of them in there, just to get a better sense of what's happening there, so you're aware of it. And I think you'll be more able to have discussions with colleagues and other people in your departments and fields. Okay, so that's the foundation on which all of this sort of sits. So what we're trying to do is move past that. We can use these tools to do other things. We can use these tools to tell stories, as long as we are, and to discover things about the world. As long as we're being truthful about where these data come from and what they're doing, then we can use them for better purposes. Okay. Anybody want to bring things up about that? I know that can feel like a complex and difficult topic, but you should feel like you're safe to bring things up here, or you can email me about them if you'd rather, but I'd love to have a discussion about that with you, if you would like to raise anything.
I mean, I guess for me, it raises like the conflict that I face in my field, because my field is very quantitative in nature. But we have what, to me, seems like a tension. For example, we rely a lot on standardized tests to kind of measure academic achievement. And yet, our field in and of itself has a lot of evidence that shows that standardized testing is not a good measure of learning, right? And so achievement and learning aren't equal, but we actually know that standardized testing is harmful. So you know, when we look at these data points to like prove it, be like, oh, okay, this part of motivation is really helpful. I always have those questions in the back of my mind.
Yeah, and one of the things that I think is really interesting is that it actually is through quantitative tools that we're able to demonstrate that these tools are racist. Right, we're able to use the tools of quantitative methods to say, look, systematically, this racial group is always scoring lower than this other racial group on this particular assessment. That's not to have anything to do with their learning capacity or their learning ability or how intelligent or smart they are. It's everything to do with how the test is designed. So by drilling down into those things, you're able to use this tool to investigate itself, essentially. Which I think that tension is very real, and I think some people probably feel it more than others within their field, depending on how much they listen to it. But particularly, you're studying equity issues, right, you said? So that makes a lot of sense that you would see that right on the front lines. So interesting.
In my program, we face very similar issues. In school psychology, we deal a lot with cognitive and achievement testing, and there has been so much studies on the bias of especially cognitive assessments, and the fact that we still have to unfortunately use them to qualify students for special education really makes our role as school psychologists tenuous, because we have to interpret that in a less biased way.
Yes, and that's really interesting too, because in that specific sense, when you're thinking about diagnostics, right, you're thinking about how does this apply to this particular kid, as opposed to most of what we do in quantitative methods, which is what happens with huge groups of people. Do you remember in intro stats where you talked about the central limit theorem and how you need bigger numbers to better approximate what's happening in the population? And we're not necessarily ever talking about what happens to one person, but we're thinking about what happens to whole groups of people, to whole populations of people. So taking that whole concept of what's happening with whole groups of people and with whole populations of people and applying it to one student is certainly a whole other layer of complexity on top of it. Gosh. They're so good and so bad. Well, I hope that you will have some tools to have these conversations with other folks if this comes up within your field. This came up on my way to talking about p-values, which is how we started today, thinking about probabilities. And I want to show you this, which don't feel too called out. Every single class I ever teach gets them wrong. This is the correct response. I don't think I've ever had more than 20% of people get this right. P-values are complicated and they're difficult. And I have 2 readings for you in the module for this week that you should read for next week as part of your homework about p-values to understand what they are. So, the idea is if there's really no difference between my groups, if there's really no correlation here, this is the probability that we would get the same result as strong of a correlation or a stronger correlation, or as big of a difference between these 2 groups, or bigger difference between these 2 groups, just by chance. If we do the study again. So if we do the study again, and there's really no difference here, what's the probability that we'd still see this effect? So, there you've got, I think there's actually 2 p-value readings and then 2 additional pieces of information about just null hypothesis testing in general. And the 2 ones about p-values talk about all the ways that people get this wrong and clarify how to interpret it to get it closer to correct. So we'll do some more discussions about that online. An online discussion is part of your homework for this week. And then we'll talk a little bit about it in class next time. Oh, look. There I am telling you that for homework you're going to review p-values. Okay. Now, next, going through this is a terrible transition. Next, what I want to talk about is, so this is a sort of strange class because it's the second in a series. And because you had a different professor for the last half of the class, so you've talked about things in a slightly different way than I'm going to talk about things. So I think it's really important for us to get on the same page in terms of how I talk about t-tests and regression and correlation. So today is a review of t-test, regression, and correlation. And while I do this, I want you to remember that this is really your first class with me. This is really your first class in GLM 2, even though you've probably had every other class 2 or 3 times, maybe even 4 if you're taking a Tuesday, Thursday sort of situation. So we're in the beginning stages of this information. That's all. All right, let's do it. So eventually, regression and GLM are going to let you do some really complex things. But first, we're going to start with something a little bit smaller. I'm going to break it down to something you're more familiar with based on your previous classes. And those things are correlations, means, t-tests, and ANOVA. So I want to start off by talking about 2 different types of relationships. So we have, on one hand, we have exact relationships, and on the other hand, we have inexact relationships. 2 variables, any 2 variables that exist can be related in one of 2 ways, either exactly or inexactly. So an exact relation is a perfect correlation. So you might have a perfect correlation when you're converting metrics. So for example, minutes in an hour. And for every single hour, there's exactly 60 minutes. That conversion is exact, it's perfect. A relation like that, if you were going to graph it, might look like this. Every 1 hour is identical to 60 minutes. So to get a value for minutes, all you have to do is take the number of hours that you want to know, and then follow the line to get to the number of minutes. So here I say 2 hours. 2 hours? This is weird. 2 hours, if you go over, that's 120 minutes. Can you think about how to express this in an equation? Just sort of jot it down on some paper if you could think about it. In this case, this is a graph, right? So I have 2 axes. I have an x-axis and a y-axis. Y is usually the outcome. So in this case, what's the outcome going to be? Uh-huh. Oh, yeah. Tiffany has the answer, but I can see it and you all can't. So what's the equation? Y, which is minutes, is equal to what?
60, right?
60x.
Yes, 60 times x, or 60 times number of hours. So y represents minutes, and so minutes is equal to 60 times the number of hours. Using that equation, you can go out to infinity and beyond. Excellent. Okay, so that's an exact relationship. For an exact relationship, there's only one value of y that is possible for every value of x. For any value of x that you come up with, 2 hours, 3 hours, 4 hours, there's only one possible y value. Okay, yeah. So, but when we have an inexact relationship, which is much more common in the sorts of things we do, developmental science, social science, education, we end up with very non-perfect relationships. So here we have, you will still get a y that's predicted, but it won't always be equal to the y actual score. So here's an example of an inexact relationship. So you see there's a big scatter of points. So there's still only one value of y that's predicted for every value of x, but any value of y is possible for any value of x. And those observed values, I think I say which one's which. The observed values can be any distance from this predicted line. Each point here represents a person or a row of data. Usually if we're studying kids, it would be one kid. If you're studying schools, it would be one school. So predicted scores are not the same as observed scores. Those are going to be different. Which one's which? Yeah. My goodness. My clickers aren't working. Come on. But just like with the exact relationship, you can still write an equation that represents the relationship between your x and your y. And you might remember this from middle school. Y equals mx plus b. That's how I learned it anyway. I think that's how my kids are learning it, y equals mx plus b. I don't have a b there, you just have an mx. To get, what are my exact and inexact things? Well, basically the b0 here is where it crosses the y-axis. So here it's crossing it at about 100. So the equation here represents where it crosses the y-axis and then the slope of it, the slope of the line. That's your expected score. So if you have an inexact relation between your x and your y variable, there is some error involved. The predicted value of a dependent variable is always an estimate of the observed value. It's not the actual observed value, it's an estimate. And here is our friend, the regression equation, which is what all of these relationships look like. This is y equals mx plus b, but written in a different way. And I'm going to show it to you a bunch of times, so don't feel pressed to get it all down right now. Here if we have b0, which is the constant, that's also called the intercept. We have b1, which is the slope of the line, and e is error. Or if you don't want to write an e being error, it can look like this. Y hat, see that little hat over the y? That means predicted y is equal to, you still have b0 and b1 times x. So in some books you read, they'll call that a y hat. In some, they'll call it a predicted y. So when we're thinking about correlation and regression, and really the GLM generally, because I'll show you they're all related, it's all about estimating inexact relations. So, what in the world is happening here? There we go. Estimating the line of best fit through that scatter plot of points is the goal of any general linear model or any regression model. The whole idea is to find the best possible line that makes the least amount of error that's possible. So how do we figure out where to put that line? I will show you. But first, I'm going to talk about the correlation, because part of finding that line is figuring out what the correlation is. Do you remember correlations? I should have asked this one on the pretest. Did you all have to calculate a correlation by hand? Did you ever have to do that? I think you did that with me. Yeah, you're going to have to do it again, sorry. You're not really going to have to do it again. You have to watch me do it again. Maybe? Sort of? All right, so this correlation is about the strength of the relation between two variables. The thing about correlations is that there's no assumption that one is the cause of the other. They are just related. Nobody's blaming anyone. It's just a thing that happened. They just go together. So here are some correlation type questions. I'm going to start with the second one. do math skills of kids relate to their reading skills? Is the amount of water you drink in a day related to a person's ratings of happiness? When I drink too much water in a day, then I have to pee all day and I'm very unhappy. Ha ha ha. So now building off of correlation, what's a regression? A regression is still the relation between two variables. You still have an x and you have a y. But again, the goal of a regression, unlike a correlation, is to predict each person's score on the outcome using the predictor. Or to predict, if it's not a person, each row's outcome. And theoretically in regression, the dependent variable is thought to be influenced by the independent variable. The y is thought to be influenced by the x. I'm going to stop short of cause, but So what's a regression? Okay, remember, with regression we want a predicted y for each person. And this is what the regression equation looks like. I've given you slightly different subscript here. Because once again, you're going to see so many different ones in all different kinds of textbooks and papers you read. So here, instead of B1, I have BYX. But here I have 3 other options. You'll see that I have, this one has a y hat and no error return. This one also has a y hat and no error return. But this one, I put the error on the end. And that error is to give you the distance between where you're predicting someone will be and where they actually are. So if you remember regression equations up here, you have an equation for line of best fit. You have the slope variable, BYX, or B1, which represents the rate of change in y for every unit of x. What's a unit? Oh, we're going to talk a lot about units. What a unit is. It's one whole number change. We'll do it again though, so hold up. B0 is the regression constant. It's also called the y-intercept. It's called the y-intercept because it's where it intersects with or intercepts the y-axis. One thing you'll learn about quantitative researchers is we're not very clever at naming things. It's called a slope because it goes up. And it's called a y-intercept because that's where it intercepts the y-axis. Okay. What's a B-weight? A B-weight is going to represent the expected gain in y for a 1-unit change in x. A B-weight on the x. And again, do you remember I said we're going to talk about this a lot? What's a 1-unit change in x? Y. It depends on what x is. So here I have, if you have a question like how many cups of coffee do you drink in cups, a 1-unit change would be 1 cup of coffee. Apparently I was watching The West Wing when I wrote these slides. The number of West Wing episodes watched, if that's the question, then the 1 unit is 1 episode of West Wing. If X's score on a math test, then 1 unit is 1 percentage point. So I'm going to take a break here for 1 second and let's talk about some of our motivation studiers. If you have a motivation scale in a large sample of people, about what would you expect the mean of that to be?
It depends on the scale point.
It depends on the scale. Do you know one in mind that you could think of? Like, is it questions like 0 to 7, do you agree to disagree sort of situation?
Mm-hmm.
So it would be like, if you averaged them, it would be somewhere between 0 and 7. So if my questions are all strongly disagree to strongly agree in a 7-point scale, then 1 unit change on that would be moving 1 point on that 7-point scale. Does that make sense? So going from agree to mostly agree, or from mostly agree to strongly agree. What about score on a spelling test? There's 100 questions on a spelling test. What's 1 unit?
1 word.
1 more question right, probably. 100 is a terrible number for a spelling test. How about 18? Still, getting 1 more, if the 18 is the total number of spelling words, is still 1 more word. Correct. All right, that's units. They're going to come up a lot, so we'll talk about them some more throughout the semester. So I'm going to walk into this first example. This is an example that's going to come up a lot during the year, I think, during the semester, I mean, where we have time from getting a PhD and number of publications that you have. This is a fake data set. You will see that I have this indicated at the bottom. This is a fake data set. And if anybody knows where I can get my hands on a real data set that has this information in it, please let me know, because I've been looking for years. I'm tired of doing fake data with this data set, but I like the example. All right, so publications and time from number of years from PhD, and each one of these is a person. So here we have 1 person who's been out of their PhD 1 year. They have 2 publications. Does that make sense? Okay. Here is person 3. They've been out for 5 years. They have 5 publications. So X, in this case, is time, years from PhD. So what would a 1 unit increase in years from PhD be? One year. 1 unit increase if X is time is 1 year. Yep. All right, so now how are we going to find the B weights? How are we going to figure out what the line of best fit is for this sample of points? We're going to find it out with equations. Do you remember me talking to you about scaffolding? Here we are in scaffolding land, where we're going to learn equations that are going to make my quant people happy, and everybody else, you can just take deep breaths and take notes and enjoy the ride. All right. What do we need to calculate B weights? Does anybody know what these mean? R, Y, X? What's R stand for? Does anybody know?
Pearson correlation coefficient.
Pearson correlation. You got it. How about this one? Yeah, you can do it. What's it say?
Standard deviation?
Yeah, standard deviation of? Of Y. And we need the standard deviation of? X. All right, we need all 3 of those things. We are also going to get these, but we'll talk about those in a second. I also gave you the answers in the PowerPoint, but still. We're going to need, oh, I told you the answer. Do you remember Y bar and X bar from intro stats? Means. So we have the mean of Y and the mean of X. And you'll see this is some basic algebra. Oh, can I make this? Look at that, yes. Here's the BYX. And BYX is also right here. So essentially you could mark this into one whole equation by using substitution. All right, so let's calculate our, oh my gosh, don't freak out. Sorry, that's a lot of information on screen at once. We're gonna do some calculation by hand. This is a correlation coefficient calculated by hand. So, to get the correlation between X and Y, we have to calculate the mean of Y and the mean of X, and the standard deviation of Y and the standard deviation of X, because remember we need those for that equation on the previous page. And then There we go. Come on. Okay. So then what we're going to do is we get a z-score for time. Do you remember z-scores? A z-score is you subtract the mean, so that the mean is now 0, instead of the mean being whatever it was, 9.6 or 7.6. Then you're going to divide by the standard deviation, so that everybody's on this nice same scale, with a mean of 0 and a standard deviation of 1. So from here, everybody has a z-score for publications and a z-score for time. You multiply them together, and then you take the mean of that, and that's the correlation. Isn't that cool? It's cooler when I make you do it yourself, but then we spend 20 minutes doing it, and that's less cool. So that's why this is like the strength of the relationship, because what I've done is multiply things together. So if this is really big and this is really big, and I multiply them together, their product's going to be really, really big. All right. So I've now gotten all those numbers from my calculations, and I can plug those numbers in. I feel like I should do a better job of showing you where these come from, but you can see that the correlation was 0.683, which we got right here, 6.8. And then here are our standard deviations of y and x, which were from here. And then, once we do this multiplication, we end up getting a B1 of 0.468 and a B0 of 3.11. So when I sub those back into the equation, this becomes the line of best fit. So all of these numbers to figure out the line of best fit come directly from each individual observation, turning it into a z-score, figuring out the relationship between those things, and then using the means and standard deviations. Ooh. All right, it's a regression by hand. Woo. What does it mean? So now you know this setup. Which one's the intercept? 3.11. That's the intercept. And the slope? 0.468. Nice. Now we can plot it. So you can see, this is a plot that I just pulled out from SPSS. It's not very pretty, but it serves the purpose. Do you remember we had 4.68 and 3.11? Look at that. You see that number right there? It's really close to 4. You can't see because my cursor's in the wrong spot. 4.68. Right there. Woo. And how do we get 3.11? Do you remember this? You go over and then up. So you end up with, that's the slope of your line. 3.11. All right, so now to these coefficients that we have. You can see where they are on the line. You know what the y-intercept is. You know what the x-slope of the line is and how to sort of get it. But what do these mean, and how can you interpret them substantively within the context of whatever you're studying? So remember, we talk about 1 unit change. So this says for every 1 year out of grad school, the predicted number of publications is going to increase by 0.468. Why? Because, keep forgetting to come over here, because for every 1 year you go over, you go up by 0.468 on this predicted line. So every time x goes up by 1, Y goes up by 0.468. It doesn't matter what your X value is, just like with our inches and, our hours and minutes, it doesn't matter what your X value is, it's the same. Now what about when years from PhD is 0, when X is 0? What's our Y expected score? 3.11. Which is, you can't see my face, it's the intercept. I remember where I was sitting, where I was like, wait, if you plug in a 0, that's why it's called B0. Ah. All right, so it means that when X is 0, the average person with 0 years from PhD has 3 publications. Remember, fake data. You're talking to me. Yes. You can also multiply this out, just like you can do with hours. You can do it with these regression equations. If X is 2, then every 2 years out of grad school, you can solve for Y and figure out what the expected number of publications would be. 2 years out of grad school, you're going to increase it by 0.93, and then you add all of these together to figure out the expected score. All right, let's see how well you've got that. So if you'll go to Carmen, you should see a quiz on Carmen. You should be able to do it on your phone or on your computer. It should be open by now. And it's only about 5 or 6 questions. So go ahead and pull it up and take that quiz. And hi, Dwani, you can take the quiz as well. This will be more like a pre-test for you, and it's fine if you don't get them all right. Because remember, my quizzes in this class is just a way of making sure that we're communicating with one another, not a way of checking you or catching you or anything like that.
Okay, I'll go ahead and take it.
Okay, great, thanks. Let's see if I can. And I'm going to pause the recording, my recording people, so that you know that I'm doing that.